We are going to do a case study about the topic the degree of polymerization impact. So it was presented by myself Deepika. The power of polymer length. So it was unlocking the material performance. Discover how the length of polymer chains measured by the degree of polymerization and it transforms ordinary materials into an extraordinary performance across the industries. So it was from the adhesions to advanced networks. Why are polymers the building blocks of modern materials? There are several types like long chain structures from simple to complex chain length matters. Let me discuss a long chain structure. So it means a polymer that are formed by linking small repeating units called monomer and it was extended into the chain. This molecules chain can contain thousands or even millions of repeating units, creating structures with unique properties. So next we are going to see about the from simple to complex. The properties of polymers are dramatically different from their constituent monomers. While a monomer might be simple liquid or as a gas, the resulting polymer can be the rigid solid, flexible film or viscous material. Chain length matters. That means the length of this polymer chain measured by the degree of polymerization is the key determinant of material behavior. Longer chain generally produces strong, more durable materials with superior mechanical properties. Molecular weight, the heart of the polymer. The long chain is simple as a specific molecular weight, but unlike a small molecules, polymers exist as a mixture of chains with the lengths. This variation called molecular weight distribution is crucial to understand and controlling material properties. So it can be classified as number average molecular weight, weight average molecular weight, distribution breadth. So in number average molecular weight, this metric represents the total weight of all the polymer chains divided by the total number of chains. So it was calculated by counting each chain equally regarding of its size. Weight average molecular weight. So it was represented as MW. This calculation weights each chain by its mass, giving greater importance to longer, heavier chains. It provides insight into the contribution of higher chains to bulk properties. Distribution breadth. The ratio mw divided by mn reveals the breadth of the molecular weight distribution. A value of 1.0 indicates all chains are identical while other higher values show greater variation in chain distributions. The distribution curve visualizing a polymer chain lengths. So it's a bell-shaped curve plots molecular weight against the relative amount of polymer at each weight. This visualization reveals the full range of chain lengths present in a sample from very short chain on the left to very long chain on the right. This peak of curve indicates the most common material weight in the distribution. So in short chain, the molecular weight will be low at the left tail of the distribution. In peak region, most common chain lengths near the distribution maximum. Next in long chain, higher molecular weight, the polymers at the right tail of the distribution. Why chain length matters? A tail of two chains. Imagine the two identical polymers with the same chemical position, but one contains a short chain while the other contains a long chain. The, sim- the single difference dramatically transforms their physical behavior and practical application. So, in short chain polymer, the brittles are easy breakable, low intensive length, poor resistance to tearing, limited flexibility. Then even in long chain polymer, it's a flexible and ductile, high tensile strength, excellent tear resistance, and greater flexibility. This fundamental difference in chain length is directly determines whether a material can be used in demanding applications like automobile parts, medical devices, or even in the high performance adhesives. Lohmann's challenge optimizing polymerization for the performance. This requires a substantiated statistical methods and systemic experimentation to understand the relationship between the process parameter and the final material performance. In design of experiments, systematic variations of reaction condition to map the region between the parameters and the outcomes. Statistical analysis. So, in the advanced statistic method to identify the significant factors and optimize the process condition. That even in the target properties, the specific adhesive characteristics like tack, peel strength, and shear resistance as the performance goals. Case study Lohmann's GmbH engineering advances with precision. So Lohmann, a global leader in adhesive type system, it was headquartered in Newland, Germany. It explains how precise control of polymer properties transform industrial capabilities into operation spanning continents and serving diverse markets from electronic to medical devices. The pressure sensitive adhesive. So in Lomel specializes in PSAs that bond instantly with light pressure, eliminating the need for heat. Then viscoelastic behavior. It means the polymer viscoelastic properties, its ability to exhibit both viscous and elastic characteristics. This behavior determines bonding performance. The impact of controlled polymerization at low months. So in control track, it optimizes the initial surface thickness for the instant bonding while maintaining a clean release properties. In peel strength, it long lasting the bonds under various conditions. In stress resistance, it developed the resistance to sliding the force for structural applications requiring load bearing capability. Assembly, medical device, manufacturing, automobile production, and consumer good packing in critical application worldwide. Beyond adhesive disparity role network polymers. In the recent research reveals that controlling primary chain dispersity in network polymer are essential in the applications for biomedical implants into the durable coating. In 2H, it extends degradation time. At higher disability can double degradation type compared to narrow distribution. In 40% increased range, wider chain length distribute expands degradation time range significantly. In the 50 years of extended potential lifespan extension for biomedical and industrial application. When network polymers contain a broader range of chain length, in degradation proceeds more gradually, while in short chain break first, while long chain maintain structural integrity longer. This controlled degradation is crucial for biomedical application where predictable material breakdown is essential. Where predictable material breakdown is essential and for the industrial coating requiring extended service life. The future is tailored polymerization as an imagination from parameter to innovation. So the tool, the degree of polymerization transcends its role as a scientific parameter to become a powerful tool for innovation. In precise material engineering, the modern polymerization technique enable precise control of chain length and distribution, opening possibilities for materials that were previously impossible to manufacture, shaping material science future. So, from the advances with specific bonding characteristics to durable networks, the ability to engineer chain length at the molecule length. As the research continues to reveal new relationship between the polymerization degree and material behavior, the future promises even more substantiated control over polymer architecture, enabling material with properties we can scarcely imagine today. So, thank you.